Greetings, Mr. Colazar's class. We're going to start out looking at the idea of ionic bonds to form ionic compounds. So today as we're going to look at the formation standard 3 of ionic bonds and how they're actually formed, kind of what the structure looks like. We'll talk about the formula unit, and then later on we're going to, this is standard 8, that's alright, to compare and contrast ionic and covalent compounds. That won't be for another section that we'll be able to finish up comparing those two. So first off, an ionic compound. A compound composed of ionic bonds, of where we get our ionic for the ionic compound. Now a compound, remember, two or more elements joined together chemically. So what is an ionic bond? An ionic bond, electrostatic, meaning our positive and negative, or the cations, the positive, and an anion, the negative ions coming together, and that positive and negative electrostatic is what holds them together. It is a fancy way of saying opposites attracting. That positive negative force is what's holding the two atoms together in an ionic compound. Now a couple words to remember. Ionic bonding occurs generally between a metal, abbreviated with M, and a non-metal, Nm. Remember, our metals, left-hand side of the periodic table, are positive, and our non-metals, right-hand side of the periodic table, are generally negative. So the positive and the negative part is what's holding them together. One exception is, however, we have ammonium, which is NH4, a positive, and a non-metal holding together. So ammonium is one of our only positive non-metals. From there, our formation of our ionic bond. So in our notes, looking at an ionic bond is formed between sodium and fluorine as an example. Sodium will transfer one of its valence electrons. Down at the bottom I've written out the electron configuration for sodium, ending in 3s1, it has one valence electron. And fluorine, 2, 3, 4, 5, 6, 7 outer electrons, all in the second energy level, 2s2, 2p5. Fluorine wants an electron. Sodium would like to give that electron away from our last section. So sodium is going to donate that electron over. As it donates that electron over, what's going to end up happening is sodium loses that electron. Fluorine gains that electron. Sodium becomes positive. Fluorine becomes negative. And it's that positive-negative interaction that holds those two atoms together. That's what we're going to know as an ionic bond. Oppositely charged particles are going to be chemically combined together. So this is an example, sodium fluoride. It's the active ingredient in toothpaste. Now to practice forming some ion compounds, one of them we just looked at, sodium fluoride, we made that formula NaF. So let's look at a second one. Calcium plus 2. Calcium, originally Ca with its 2 outer electrons, and chlorine, group 17, 7 outer electrons. Now calcium is going to want to donate or give away 1 electron to chlorine. Chlorine now has its 8 electrons, however calcium still has 1 left over. What ends up happening is if there's 1 chlorine atom around, calcium will eventually seek around and find another chlorine atom with its 7 outer electrons, and it will donate its other electron to chlorine. It's lost 2 electrons, that's where that plus 2 comes from, and chlorine minus 1. Now when we write this chemical formula out, we have 1 calcium, Ca, and we have 2 chlorines, Cl2, with the subscript down below showing both of our chlorines. Each chlorine would have a negative charge, and our 1 calcium has a plus 2 charge. Another way we could look at this, aluminum has a plus 3, oxygen has a minus 2. Now, to get these two to combine together, lowest common denominator between the two is 6. One way we could look at it is if we need to get to 6, 3 times 2 would give us a plus 6. 2 times minus 3 would give us a negative 6. So we'd actually need, as we're going, so to show that out, times by 2 gets us to a negative 6, or positive 6, excuse me, times by 3 would get us to a negative 6 to keep us overall neutral. One way we could show that instead is that we need 2 aluminums and 3 oxygens, or we can do what's called our crisscross method, where we're going to take that 3 and say that we need that many oxygens, and this 2, not the charge, but just the number, and that's how many aluminums we need. And in the end, aluminum, 2, oxygen, 3 would be our chemical formula for aluminum oxide, Al2O3. So in the end, we're still neutral. We had 2 aluminums plus 3, so plus 6 total. 3 oxygens and minus 2 gets us to minus 6 total. So that's the beginning of our formation of ionic compounds, giving and taking of those electrons to make those charged particles. Polyatomic ions. Poly word means many. Atomic, atoms, ions, charged particles. So many atoms that are ions, positive or negative, and they behave similar to a single atom. So anytime we see our polyatomic ions, we're going to see a lot of them in our gold packet coming up. An entire second page has a bunch of our polyatomic ions, so we'll see a bunch of those. Anytime we see those, like ClO3 is a group of atoms with a negative overall charge. NH4, group of atoms with a positive overall charge. We're going to treat those as a single atom. So using our crisscross method, if there's no number, it's 1. We're going to crisscross. So in the end, Na plus ClO3. Now notice again there's no overall charge because the positive and negatives cancel each other out overall. So sodium hypochlorite or chloride is what we know that one to be. NH4, our positive ion. Our Cl, our negative ion. In the end, NH4, ammonium chloride, active ingredient in ice packs. NH4Cl or ammonium chloride is what we'd have there. Now for our next one, magnesium and phosphate combining together. This is where we have a plus 2 and a minus 3 again. So the 2, we're going to say we need 2 of these and we need 3 of these. Now the first part, magnesium, Mg3, is what we'd have. However, this part's where we're going to see PO4, but we need to show we have 2 PO4s. So a rule coming up is going to be, we're going to put it in parentheses and the 2 on the outside, showing that we have 2 PO4s and 3 magnesiums to keep us overall neutral charge. And our last one, NH4, ammonia plus SO4. As we move back, NH4 would be our plus part. We have 2 NH4, so we're going to put the parentheses around NH4 and 2. And we have 1 SO4, so we don't need to write any number there. 1 SO4 would be our chemical compound for ammonium sulfate. So again, polyatomic ions, 2 or more atoms that behave as a single atom that has a plus or minus charge. So our ionic compounds. Ionic compounds have very high melting points. They're very hard, so they're hard to scratch, would be a way to say that. So ionic bonds are strong, require large amounts of energy to break that positive and negative bond apart. Ionic bonds have what are called crystal lattice structures. It's a regular three-dimensional pattern of those positive and negative interactions between them. So as the positive negative, so it'd be a repeating positive negative pattern, so that the positives would join up with the negatives and the negatives would connect next to the positives. They make many regular three-dimensional patterns. They might make a square shape, or many other three-dimensional patterns are how they actually make. If you look at table salt, it actually makes a nice little cubic structure. However, they're very brittle. They can be easily broken. We said that they were hard to begin with, but once enough force is applied, they can actually break very easily. What I would like you to do is to draw out in number 10 in your notes the picture we have here, where we'd have a circle would be our positive ion, next to a negative, next to a positive, and keep alternating so our negative is next to the positives, and each positive is surrounded by the following negatives. So we have a repeating crystalline structure. Three-dimensionally, this is what sodium chloride looks like, with sodium being the blue and chlorine being the green, where they would repeat. So each chlorine is surrounded by sodiums, and each sodium is surrounded by chlorines, the positive and negative, positive and negative. Now the problem is it's held together very strongly, but if we were to take and apply enough force to it, so you're going to apply a force to the picture, you're just going to draw a nice little hammer in or something to hit our object with, and as you actually hit that object, if you apply enough force, those objects or the atoms are going to move over. And if they move over, notice how the positives are now lined up and the negatives are lined up. And we know that opposites are going to repel each other. The positive, negative, the opposites attract each other, likes repel each other. So once we get those two close together, the positives are going to repel each other, and it's going to cause it to split apart. We're going to force those apart, the positive interactions, and by brittle what we mean it's going to break apart. It's going to shatter or fracture very easily. So make sure that we include all of that drawing and information in number 10. You'll need to know about why ionic compounds are brittle. They're strong, but they're brittle with that three-dimensional crystal lattice. The last info is about the ability to conduct electricity. Now, a couple scenarios. Ionic compounds conduct electricity if they're melted or dissolved in water. Those positive and negative are allowed to allow electrons to flow between them. If they're in the solid state, those particles are not free to move and the electrons are not free to move between the positive and negative portions. So ionic compounds can conduct electricity when they're melted or dissolved in water, cannot conduct electricity if they're in their solid state. Ionic compounds, neutral overall. So we've shown so far equal parts of opposite charges. If you have a sodium that's a plus, it's going to combine plus with fluorine that's a minus, and they're going to combine 1-to-1 ratio, so overall sodium and fluoride would be balanced. So overall the compound's neutral even though it's made up of positive and negative charges. Our other example, aluminum had a +2, oxygen a -3. So when they combine together, showed the crisscross, that they make aluminum oxide. Sorry about that, that's a +3. Oxygen's a -2. Please make that edit. So when they crisscross, we need 2 aluminums. 2 times 3 is +6. 3 times -2 is -6. But overall, it's a neutral particle. And to end with today, got a little cartoon here. It says, from the teacher in the room, perhaps you gentlemen would mind telling me what you just find outside the window is so attractive. We have all of our positive ions, lithium, potassium, rubidium, and cesium from group 1, and sodium are looking at the halogens outside. Nice and attractive there. The bromine, chlorine, and fluorine, the negative charges. The negative charges are attracting to the positive charges.